Quantum mechanics is the fundamental theory that describes the physical reality. The philosophy of science dictates that any scientific theory must account for any observations in the real world. Despite the triumph of classical physics for more than 2 centuries, it eventually disagreed with experimental observation. Two of the most important ones are the photoelectric effect and the double-slit experiment. Two types of distinctively different objects in classical physics are particles and waves. However, the two experiments above demonstrate that the fundamental objects of the material world behave as both. Thus exhibits what's known as the wave-particle duality. The result of experiments hint at the more fundamental and intricate theory of reality. Classical mechanics was therefore replaced by quantum mechanics. However, classical mechanics remain as a useful approximation at the macroscopic scale, and we'll show in Chapter 5 that quantum mechanics is consistent with classical mechanics. Classically, if we want to describe the dynamics of the system, we need a set of 6 numbers, position in 3 directions and momentum in 3 directions. If we know where the object is and how fast it is moving, we can predict its position and momentum in future by Newton's laws of motion. At the scale of atoms and molecules, the system becomes extremely sensitive to the surrounding environments and become easily influenced by random fluctuation, which are normally negligible at the macroscopic scale. In addition, for us to gain knowledge of the system being studied, we interact with the system, which invariably disturbs the system. The disturbance may be again negligible at human scale, but significant at small scale. Appreciating the complex nature of the physical state of an entity at small scale, we may need infinitely many numbers to fully encode the information of the object in the form of a probability distribution due to the fundamental indeterminacy introduced by the disturbance of the system of interest. The concept of a complete set of amplitudes represents the full knowledge of the quantum entity we are interested in. The essence of the complete set of amplitudes is that we can extract any information we want from the set. There's nothing left to know about the system apart from it. When we have a list of numbers, it is natural to think of the list of numbers as a vector, where the components of the vector are the amplitudes in the complete set. The vector is effectively a container for all dynamical information of the system of interest. This vector has the dimension same as the number of amplitudes in the list. As the list may be infinitely long, the vector can be infinite dimensional. As these vectors are very different from the usual 3-dimensional vectors that we are familiar with, they have earned their own notation. We change the arrow above the letter to an angle bracket to the right. This is called a ket vector, or simply a ket. As this vector fully encodes the dynamical information of the system, it is also called a state vector. Thus, ket is the mathematical representation of the physical state of the system, the quantum state. We have arrived at the first postulate of quantum mechanics. The quantum state is represented by a ket. These kets add and multiply by numbers like ordinary 3D vectors, thus they form their own vector space. We can also use our intuition for 3D vectors to these abstract state vectors. The square length of the vector is given by the sum of the modulus squares of all amplitudes, as we allow the amplitudes to be complex numbers. The equation is obtained by generalizing the Pythagorean theorem to infinite dimensions. As we have encoded all the dynamical information into the components of the ket, the richness of the information is in the orientation of the ket in the infinite dimensional space, which I'll refer to as the Hilbert space from now on. The length of the ket therefore encodes no information and can be set to 1. In other words, we can scale the entire set up or down by a constant factor without losing information. We also know the sum of probabilities of all possible outcomes of an event is 1. As now we have fixed the length of the ket to 1, it will always remain 1 no matter what happens to the system. As the probability will always remain 1 no matter what, we have established a connection between the total probability and the length of the state vector. We have used these amplitudes at the start to encode the information of the system in terms of a probability distribution. It is no surprise to us that there exists a close connection between amplitude and probability. Comparing these two equations give us the modulus square of the amplitude is probability. This is called Born rule. we have arrived at the second postulate of quantum mechanics. Probability is the modulus square of the amplitude. Strictly speaking, postulates cannot be derived from existing facts. They should be accepted without question. All we should be concerned is whether it accounts for observations in the real world. However, I have deliberately tried to motivate these postulates to give you some intuitive satisfaction in the fundamental framework of quantum mechanics. A more rigorous approach is to state all the postulates at the start and construct the rest of the quantum mechanics from there. It is natural for us to choose a basis for the ket representing the state of our system. We write the ket as the sum of basis kets. This is analogous to writing a 3D vector as a linear combination of the unit vectors in x, y, z directions. A linear combination simply means multiply each vector by a constant, then add the result. This sum is called quantum superposition, another fundamental feature of quantum mechanics. Quantum superposition is what ultimately gives rise to the linear algebra framework of quantum mechanics. To discover the physical meaning of the basis ket, we construct a concrete example. Allow AI to be the amplitude of finding the particle in the ith potential well, where AI mod square is the probability given by Born rule. If we now set AI to 1, ket psi becomes ket I, and we are certain to find the particle in the ith well. Hence we could conclude ket I is a state of particle definitely being in the ith well. Our choice of potential well as an example is arbitrary. We equally could have used energy levels or any other measurable quantities to illustrate the same point. Thus, the basis kets are states of certainty. It is reassuring that basis kets are the simplest possible states, and they combine to give rise to complicated states with uncertainty. So far, we have encoded all the dynamical information in the ket, in which the amplitudes are the components of the vector and are closely related to a probability distribution that we seek after. So our next goal is to extract these amplitudes from the ket. In other words, we need a set of functions that input infinite dimensional vectors and output a complex number, which is the component of the basis ket. We now introduce a new notation for these functions of left angle brackets, which is called a bra vector, or simply a bra. Hence, if we have left and right angle brackets strung together, we have a bracket. This is known as the Dirac notation, and its power will be apparent shortly. To proceed, we'll ask the question of, what is the amplitude of the system being in the ith well, given our system is in the jth well? The answer is, being in different wells are mutually exclusive events. The amplitude is 1 if I equals to j and 0 otherwise. We can define the Kronecker delta using this rule. We now have a neat expression of the orthogonality and normalization of definite states, collectively known as orthonormality. We use this equation to define the basis bra. Any generic bra can be expressed as a linear combination of basis bras, just like a generic ket can be expressed as a linear combination of basis kets. The word orthogonality hints at the connection to orthogonality between vectors in 3D space, and there's indeed a close analogy between the two concepts. The standard basis vectors in 3D space are mutually orthogonal to each other and normalized, where EI is the ith basis vector. Conventionally, I equals to 1, 2, 3 for x, y, z respectively. We now ask the question of, what is the amplitude of the system being in the ith well for an arbitrary state ket psi? We show that it is mathematically represented by bra I ket psi by expanding ket psi in terms of its basis, which are definite states of being in the well. Then we use the linearity of bra to pass through the sum, as bra is a function on kets rather than numbers. The bra I ket j is the Kronecker delta and vanishes unless j equals to I. Therefore the sum contracts to a single number, ai. Thus we have proved the amplitudes of the system being in the ith definite state is given by bra I ket psi. In other words, if we wish to obtain the amplitudes of the system being found in the ith definite state, we left multiply the system's ket by bra I. It is worth noting that we must use a different index for the sum. This is because the bra does not have to correspond to any arbitrary basis ket that's being summed over, but may correspond to a specific basis ket. Intuitively, we know that the component of an arbitrary 3D vector in a direction is given by the projection onto the unit vector of that direction, mathematically given by the dot product. Comparing these equations shows that the bracket has a close connection with the dot product in 3D space. We therefore generalize the dot product to space that may be infinite dimension to the inner product, and angle brackets are in fact borrowed from notation of inner product in math. Vertical bar can be interpreted as given in conditional probability. The dot product of a vector with itself gives the square of the length of the vector. By analogy, the inner product of a ket with itself also gives the length square of the ket, which must be greater than or equal to 0. Thus, given an expression for the ket as a sum of its bases, we must define the amplitude in the bra to be complex conjugate of the ket. Otherwise, the length may not be positive or even real. If we have two kets defined as below, then two possible inner products are bra phi ket psi and bra psi ket phi. Taking the complex conjugate of the right-hand side of the top equation gives the right-hand side of the bottom equation. This means that the complex conjugate of the inner product is the inner product with left and right argument swapped. At the start, we said the ket representing our physical system must have unit length. If a ket does not have length of 1 to start with, we can always normalize it by dividing the ket with the square root of the inner product with itself, which is analogous to how we would normalize a 3D vector. Everything we discussed so far assumes a discrete spectrum, such as individual potential wells and energy levels. However, some quantities are not discrete. For example, position of a free particle is a continuous quantity. To incorporate this into our mathematical framework, we note that the integral is the continuous analog of a sum. We write the general state ket psi as a superposition of definite states of position ket x as the following integral, where the coefficient is now a function. The coefficient function is called the wave function. The modulus square of the wave function is the probability density instead of probability in the discrete analog. The inner product is, by analogy, the integral displayed on the screen. The Kronecker delta expressing the orthonormality of the basis ket is now replaced by a Dirac delta. Dirac delta is a rather strange function. We'll look at this function in more detail in the next chapter. A vector can be described by various coordinate systems. Two of the most common are the Cartesian and polar coordinate systems. Each coordinate system assigns a different set of numbers to describe the same vector. Thus, the description of the vector itself is not unique. A ket can be described by various ways by choosing different basis kets. Representation is the choice of basis ket. Quantum state itself is independent of representation. Position representation is when we choose definite state of position ket x as the basis ket. Momentum representation is when we choose definite state of momentum ket p as the basis ket. So on and so forth. A physical system has three ingredients: states, observables, and dynamics. We have now understood how quantum mechanics describes the state of a system. In the next chapter, we'll begin to discuss how the observables are represented in quantum mechanics.